Hey, we're Neurotech at Davis. My name is Kushal and I'm the president.
Hi, I'm Priyanshi. I'm co-head of project.
My name is Ayush. I'm the other co-head of projects, and we're excited to present NeuroAssist, a brain-computer interface that uses eye movement to facilitate communications for people who are physically immobilized.
We have three main parts to this project: data streaming, signal processing, and hardware interfacing. For the data streaming part of the project, we're using the Muse 2, which has 4 electrodes that can directly stream brainwave data. So we're using that. We're using the raw EEG signals and using a fast Fourier transform to translate this data into brain frequency data so we can use it to create a brain-computer interface. To do this, we created a supervised machine learning model that's able to take the values and train it real time and send those continuous values over onto a Raspberry Pi. We used socket programming to do this. We have the server side set up on our computer and the client side set up on the Raspberry Pi. Essentially, the server side on the computer averages the values of our decision and sends over continuous values to the Raspberry Pi, which is able to make a decision based on the input and output in either a red light bulb, a green light bulb, or a buzzer.
So this device is primarily designed for those who suffer from paralysis or those who suffer from neurodegenerative diseases that impact speech and mobility functions. With these impediments and these limited mobilities, oftentimes these patients can't express themselves properly or even call for help when they really need to. Our brain-computer interface allows these individuals to respond to simple yes or no questions and also call for help using only eye movements. So the way this works is just how you shake your head from side to side to say no. Simple lateral movements with your eyes would trigger the red light bulb, which would be interpreted as a no response. And just like how you nod your head up and down to say yes, up and down eye movements would trigger the green light bulb, which would be interpreted as a yes. To call for assistance, you would simply need to blink rapidly, which would trigger a buzzer and alert anyone who wasn't in the room with you. And our last and final state is the baseline, or rest state, which is basically when your eyes are open with limited stochastic eye movements.
So this is our circuit for our project with the red light bulb, the green light bulb, and our buzzer. And so I'm going to go through how this works. This red wire here is connected to the 5-volt GPIO pin, which is always on the Raspberry Pi, and is connected to the positive supply bus on the breadboard. This white wire over here, which connects to this black one over here, is on the ground pin on the GPIO, and it's on the negative supply bus for the breadboard. The rest of the wirings on the Raspberry Pi are connected to each of these. So the yellow wire here you can see is connected to pin 7 on the GPIO, and it's connected to just on the circuit for the red LED bulb. So this is the positive side. You can see the resistor, the bulb, and this is the negative side of the same red light bulb circuit. Then for the green light bulb here, we have the brown wire connected to become the positive side. So we have it already connected to pin 11 on the Raspberry Pi, and we have it connected to the positive side of the green light bulb. You can see the resistor again, and then the blue wire for the negative side. Lastly, we have this black wire that connects to the circuitry for the buzzer, and you can see that this side connects again. The circuitry for the buzzer was slightly different than for the ones for the bulbs, but it has a resistor and a transistor involved, and we have this as a negative side, and we have the 3 wires going that complete the circuit for the buzzer.
Here's a live demonstration of how the BCI works. When she moves her eyes from side to side, we see the red light bulb glow. When she moves her eyes from top to bottom, indicating a yes, we see the green light bulb glow. And then when she blinks her eyes rapidly, we hear the buzzer. Then again, when she moves her eyes up and down, we see the green light bulb glow. And then when she moves her eyes from side to side, we see the red light bulb glow, indicating a no. When she doesn't move her eyes, everything is turned off. This is an interactive demo with the NeuroAssist, Ayush will be asking Priyanshi questions and she'll be responding using the BCI.
Hey Priyanshi, are you hungry? Red light, I guess that means no. Hey Priyanshi, are you thirsty? Green light, means she is. Here you go. Oh no, she needs help. Here you go.
We're streaming the data from the Muse to a Mac over Bluetooth. Because the Muse headset uses Bluetooth Low Energy, it is not compatible with the native Bluetooth driver on the Mac. So to establish connectivity, we have to use the BLED112 dongle, which is this little thing that you're seeing here. After you've connected that to your computer and established Bluetooth connectivity, we used the Muse LSL library to initiate a stream, and we used PyLSL to create an inlet and pull that stream from the Muse.
To train the classifier, we're recording 20 seconds of data for each feature. Imagine this is the data that we take. Then we divide this data into epochs of 1 second. Let's take an epoch length from here to here. The next epoch we take is going to have 0.8 seconds of overlap with the previous epoch. This distance from here to here will be 0.8, and the new data that we're adding to the epoch every time is 0.2 seconds. After we divide the data into epochs, we compute the band powers of each epoch of each feature. So in total, we have 4 feature matrices with epochs and corresponding band powers. We then feed those feature matrices into our multi-class machine learning model, which in this case is a random forest classifier.
So now that our model is trained and our classifier is ready, it's time to actually start getting the classification outputs that we need. So we have a buffer where we store 5 seconds of data at any given point in time. The buffer is continuously updated 0.2 seconds of data at a time. We first start off by applying an entire bandpass filter, more specifically a Butterworth filter, on the entire buffer. From the buffer, we take out epochs, and once the new epochs are created, we compute the feature vectors of each epoch by applying an FFT. After we get our feature vectors, we then pass them into the model that we just trained, and from that we get our classification categories, 0 to 3, for the 4 categories that we have.
In order to get our BCI project to work, first we have to stream data directly from the Muse to our laptop using Bluetooth. So you can see here we did Muse LSL stream, which found a device, connected to it, and shortly it's going to stream data directly from the Muse. And I'll say that by saying streaming data. Okay, so now you can see that it's streaming the EEG. Then on 2 separate terminals, we'll have the server and the client program. So the server will be on the purple side. So when we run our script, Python BCI classifier, I set the training length to 5 seconds, so it's not an accurate training, but it'll instruct the user to enact the 4 different features, so keeping their eyes open, moving their eyes side to side, moving their eyes up and down, and then just blinking rapidly. And on the client side, we'll first SSH into the Pi, which will ask us for a password. And once we're in the Pi, we can run the circuit program. And now you can see it taking the data from the server side and transporting it to the client side and classifying it into different features, which currently are not accurate, but when we actually train it for 20 seconds, these will be accurate features.